This example comes out of section 7.1, Characteristics of Exponential Functions. This example comes out of 7.1, Exponential Functions. We're given some information right at the start that a certain bacteria population triples every week. More commonly, they'd give us a doubling time for bacteria, but just to give us a more interesting situation here, we've got tripling so that we have a base other than 2 for a change. So we asked a few questions. The first piece of this is write an equation for n versus t, where n is the number of bacteria and t is our time. We're assuming there's one bacterium to start. So our equation is a relatively simple exponential equation. N equals 1 times 3 to the exponent t, where t is just our number of weeks. If we're not sure our equation works, try some numbers. After 0 weeks, we have 1 bacterium. After 1 week, we have 3. After 2 weeks, we have 9. So it's tripling every week. Second question. We're asked to sketch a graph of n versus t. So we need our time in weeks on our x-axis, our n, our number of bacteria, on the y-axis. I'll just do it for the first few weeks. On week 0, we have 1 bacterium. On week 1, we have 3. Week 2, we have 9. Week 3, we have 27. So our scale needs to be somewhat appropriate so we can see those points. A good question is, should I connect the dots as I did in a last example where we had radioactive elements decaying over time? In this case, the answer is yes and no. We do have continuous time on the x-axis, so you can have 1 week or 1.2 weeks or 0.98 weeks or any fraction of a week that you want. But for number of bacteria, you can't have half of a bacterium. A bacterium is a living creature, organism, like a person is. So a population of a city can't have 0.5 or 0.2 or 0.3 of a person. Population of bacteria can't have 0.2 or 0.5 of a bacterium. So we would have numbers in between, 1 and 3 and 3 and 9. And so we would have dots in here, and the overall shape would be that of an exponential curve, but it would not be a continuous line. So that's emphasized down here below in the next question, which says, tell me what the domain and range are for this. So if we're asked the domain and range for a function like this, our domain has to do with our time values. So what can time be, what can't it be? Well, in this case, time has to be greater or equal to 0. Negative time doesn't really relate to this example. Other than that, time can be any real number, because we can have fractions of weeks, months, days, seconds, whatever. Now our range is a little bit more interesting, I think. It's n, the number of bacteria. N definitely has to be greater or equal to 1. That's the lowest it ever goes. But it's not all real numbers, because we don't, again, have fractions, decimals, etc. We need to say n is an element of, and here, because we've already said it's greater than 1, you could say integers, whole numbers, natural numbers, and they would all be fine. Since we've used integers before, we can use it here since we've said it's greater than 1. The last question is our kind of a little application question, and it's, how many days will it take before there are 16 bacteria? Well, algebraically, we'd be looking at, when does 16 equal 1 times 3 to the t? Or just, when does 3 to the t equal 16? The answer is not sure, somewhere between 2 and 3, right? Algebraically, we'd have to use logs, and we'll learn that later on in the course. But for the moment, I'd be looking for you to graph the left side, graph the right side, which you already have done up above, but y equals 3 to the x. It'll give you 2 graphs that will, at some point, intersect each other. It's not going to be after 2 weeks, because after 2 weeks you only have 9 bacteria. And then after 3 weeks you already have 27. So it's some number in between. So you need to find the intersection. Make sure your window setting is big enough. So maybe make sure this goes from 0 to 20. This one goes at least up, maybe up to 5 would be big enough. When I find that intersection, I find that it's about 2.52. Now, I do need to remember what I'm talking about here. The question said how many days until there are 16 bacteria. What I defined time as on this graph was number of weeks. So this is 2.52 weeks. So you would need to, do the not too complicated calculation of multiplying by 7 to say, okay, there's 7 days in a week. And so that would give me approximately 17.6 days. If this was a numerical response, the rounding would matter. They'd, say round to the nearest day, or to the nearest tenth of a day. But here we haven't said anything like that, so we'll just leave it as it is, 17.6 days.